Okay, hello everyone. So I'm here for my unscheduled talk for QPL, where I'm going to present my work about classical and quantum network coding. What are the links? What are the difference between them? Which is a story about tensors by myself and my advisors, Frédéric Grosshans and Damian Markham. So let's get down to business and look at this idealized figure of a quantum network. So idealized because each edge here represents a perfect quantum channel or a maximally entangled states, which are equivalent view of it, and of dimension that can be higher than 2. And each node here, represented by the purple dotted circle, can operate quantumly as they want on their qubits, the qubits that are inside the nodes. And they can communicate classically freely with each other. That's some kind of idealized picture of a quantum network. And over this network, several nodes that we will call the clients of the network will want to share a pure state in order to, for example, it could be EP pair to QKD or GSZ for conference agreement. They will want to share some quantum pure states to be able to perform some quantum application. We choose the clients of the network being the leaves of this network. This is a choice made arbitrarily, but not so much since, for example, if we want these nodes to be a client, we can add some artificial leaves to it and design it as the client. So for simplicity, for the sake of simplicity, we consider the leaves of the network as the clients of this network. And those clients, as I say, will want to share a pure state between themselves. So it could be, of course, a multipartite entangled state, for example, a four-partite entangled state here, or it could be a product of two bipartite entangled states. They can want to share an EPR from here to here and another EPR from here to here. The question is, the topology of the network gives you certain resources. You have a limited amount of channel. The big question is, given a topology of network, which distribution are possible? That's a question that's not only present in quantum networks and quantum information theory. That's a question that were already asked in classical theory. And some workarounds have been found. For example, to go beyond routing simply, for example, source 1 wants to communicate a bit to sink 1, and source 2 wants to communicate a bit to sink 2. If they do routing, they cannot perform this film. But if you allow the nodes to perform arbitrary arithmetical operation over their inputs, for example, intermediary node 1 here will get inputted byte 1 and bit 2 and will output the XOR of the two. If you allow that, as you can see on this scheme, S1 can transmit a bit to T1 and S2 can transmit a bit to T2. So this network is the so-called butterfly network, and it's a classical example of what network coding can do and how it can perform some distribution that routing cannot. Why am I talking about classical network coding? Because it was fun. So it was a paper made by Kobayashi and Local, which linked classical network coding, some distribution of classical network coding. For example, you output IA, you input IA and you put out IA here, etc. Could be linked to some quantum protocol, some LOCC protocol. LOCC stands for local operation and classical communication, is the setup I presented before. And for example, if IA can transmit a bit here, they can share an EP air. And actually, there's an implication that if there exists a classical network coding on the topology of network, you could find a quantum network coding on the quantum network presenting the same topology. So it was presented in Kobayashi and al., a perfect quantum network communication protocol based on classical network coding. what we will have here is we want to know, what was left open was that if a quantum network coding imply the existence of a classical network coding over the same network, the equivalence. We decided to extend a bit the notion of quantum network coding. In the Kobayashi and Legal and after, what was called quantum network coding was the LOCC, so local operation classical communication. We consider that a state psi shared by all clients can be distributed over the quantum network if psi can be distributed by a stochastic LOCC protocol. What does it mean by stochastic? Is that we consider the protocol can abort, but as long as the protocol can succeed with a probability superior to 0, no-null probability, then we consider it a success. And that's the first result where, to start, we were only interested in quantum network coding. And we found, so it was inspired by the tensor network formalism, that if for this network, for each nodes inside the network, so non-client nodes, I associate a tensor with dimension corresponding to the incident edge of this network, and that I collapse those tensors alongside alongside indices represented by the edge shared by the two nodes, as you see here. If A and B share an edge, I will collapse them alongside the edge. Then, so for a quantum network and what we call distribution tasks, so it's the description of the states where we put every coefficients of the state into one big tensor. So if this tensor, we consider it achievable by quantum network coding over the network, if and only if it can be factorized by this set of tensors where each of those tensors is associated to a node of the network with coefficient in the complex field, and that those tensors are contracted along indices corresponding to shared edge. That's the first result, even inspired from tensor network from formalism. And already with this result, we managed to find a proof that, so we took some kind of butterfly network and kind of tearing the wing. And the goal was to see, was there a possibility to going from a square network and to share cross EP pair along this network. Of course, with probability 1, it's impossible, but where is there even a non-zero probability to do that? And from this formalism, we managed to see that there was no factorization that was possible. And so the transformation was not possible. We found that there was already a proof of this, but our proof is much more compact. It's make 1/2 page in 2 columns, and much more able to generalize since we have this factorization condition. We go back to classical, because as I said, we wanted to establish the difference or the relationship between classical and quantum network coding. And since we extended the quantum setup by allowing protocol to abort or having some probabilistic output, we also extend the classical network coding by introducing some stochastic classical network coding, which means that based on their inputs, the node can probabilistically decide what the output will be, or it can abort also. Each node can choose based on their input to abort the protocol. The new distribution task, before the distribution task was the coefficient of the quantum state. Here, it's based on what is input on the network. The distribution task is the conditional probability on what the output of the network will be based on the inputs. And as before, we can associate to each node of the network a tensor, but this one will be a tensor in R+. Why is that? because it will be the operation that the node will do based on its inputs, for example. So as before, A got 2 inputs and will decide probabilistically what it will do with those inputs. And we have our second theorem, which be for a distribution task. So a classical distribution task will only have coefficient in R plus up to some normalization to have some probability. And it's said achievable by a stochastic classical network coding, if and only if this distribution task can be factorized by associating tensors with appropriate dimension to each node of the network, a tensor with coefficient in R plus, and where tensors are contracted along indices corresponding to shared edges. And we have a third theorem, which kind of an extension of the work by Kobayashi and François, which is any distribution task achievable on a network by a stochastic classical network coding protocol is achievable on the corresponding quantum network by a quantum network coding protocol, which means if your tensors is factorizable in R plus, of course, it's factorizable in C. So it's not a problem. And a direct application actually of this is that we can find on the classical counterpart of this network a way for the two sides here to share a bit, the same bit, and the two sides here to share a bit. The condition is that we need to have ternary channel in 2 of the channel, which means based on the previous theorem that we can find a LOCC for to go from this quantum network with maximally integral state of dimension 2 here and here and 3 here and here to a cross EPR pair with probability 1. So there's a direct correspondence that is, there's some application that can be done with that. So to remind what we have, quantum network coding means factorization in C. Classical network coding, factorization in R plus. If the T is a non-negative tensor, which means a tensor with coefficient only in R plus, we consider the distribution of the associated quantum state by looking for a classical protocol. And actually, the quantum states that are represented by a non-negative tensor are called the quantum subset states. So it's actually a quite large family of states, and it encompasses all GSZ states, W states, or at least any bicolorable graph states. The question is, for the difference, is there some non-negative tensor T, which can be factorized in C, but not in R plus? So that's the previous question. Is there some quantum network coding protocol that have no classical equivalence? Actually, yes. And it can be seen easily. There exists a channel with quantum network coding and no classical network coding, which is the typewriter channel. So you have a channel of dimension 3 on which you try to pass some kind of quartz. You cannot do it in classical, but you can do it probabilistically with the quantum. Compression of a typewriter channel through a Q-treat is possible, but not to a treat. So that's the end of my talk. Thanks for everyone. And I leave you with a small summary of that and also the link to the archive paper. Thank you.